So compare this. I'll just hit it with yellow chalk. And these little T's were what? Here's T. And you could have put this on any other axis. So how could you do this one? X squared. Y squared plus Z squared. Try that. Here, I'll erase this. How would you set that up if you want to do it like this? What would you get?
Tx.
So I'm going to get a cone. It's going to be centered on the x-axis. Okay, you're T. And then it's going to be what? T cos theta in. T sine theta. That circle just keeps getting bigger and bigger and bigger as T increases along the x-axis.
Okay.
Right? And it makes that double cone. T can be negative. T can go negative. It does not have to be that parameter. It doesn't have to be positive values. Super job. Hey, who else was big time in 12.6? For what? The sphere. So again, we're going to do the sphere two different ways. Sound good? So when you got it, we're parameterizing all the common surfaces. After this, we pretty much hit them all, right? I don't think we're missing any other weird ones. I'll erase this. How about a sphere? How about a sphere, everyone, with a radius of 2? Sphere. A sphere with a radius of 2. There's the parametric centered at the origin. There's a sphere. I'll erase the cone picture. That's a sphere centered at the origin with a radius of 2. Sphere centered at the origin. Right? Can you come up with a parametric representation of? How about the top hemisphere? Can you come up with just a parametric representation of that top hemisphere, just the top, and project it onto the xy plane? I don't think you'll find that hard at all. You want to use x and y? Sounds pretty easy to me, right? Let x equal x, let y equal y. You got these little x and this little y, but what's in this last component? What would z equal? 4 minus the x squared minus the y squared, and what should I put on top of that? There you go. You just parameterize the top hemisphere. How about that? Not bad at all. So a lot of times you'll do this. But not always.
Can you ever go polar if you need to be?
You sure can.
You can.
A lot of times, everyone, because we're going to be eventually doing surface area, we're going to find surface integrals, and we'll be doing these double integrals. And so if that projection is a circle, we're definitely going polar. But if it's a flat plane, like when we get the surface area of just a flat plane, we're going to be like, keep that Cartesian. But you're definitely right. And I can deal with this, something like this, because that projection is a circle. We're going to want to go polar. But on that note, polar in three-dimensional space became cylindrical coordinates. What was that other coordinate system we used? Spherical, right?
Spherical,
So when I want to show you there's another way to do a sphere. By the way, does everyone know how to parameterize the lower hemisphere? Just make this a what?
Negative.
Negative. So one more thing. Here's another way to parameterize a sphere. Which would be, we just got to recall, do you remember? Spherical coordinates. What did the x component equal? So I'm going to use, here's my two parameters. How about theta? Do you remember this dude? Remember phi? I can parameterize a sphere this way, using spherical coordinates. Now, the only thing about this is going to look long. So here we go. We need enough space. That should do it. All right, what was the x component? It was radius, or we call it rho. What's the radius of the sphere? 2? 2. And that was what? Sine phi cosine of theta. What was the y component? 2 sine phi and then a sine theta. And do you recall the z component? It was just 2 cosine of phi. And I just parameterized the entire sphere surface using spherical coordinates. So that's another way you can do a sphere. If you're curious which way am I going to have to do it, it depends on the math problem. It will depend. You're going to find partial derivatives eventually in a couple of minutes. And you go, well, what's easier to find the partial derivative to? Sometimes you may just stay with those x's and y's. But this is another way to parameterize the surface. Cool. So, hey, I think we've hit all the major ones, right? Sphere, cone, cylinder, paraboloid, plane. Again, I don't want to throw you off, but what surface is this? Trick question. What surface is this? Trick question. What surface is this? Trick question. That's not, yes, that's not a surface. Not a surface. What is this? And I heard it. It's some kind of, I'll drink that surface with a V. It's not a surface. It's some kind of curve. And you said this is a straight line. That's a line. So that's a parametric representation of a line. We parameterize a line that way. Cool. And there's one more I did want to show you. So it's best us, we don't have to draw this, but we can recognize it. Do you remember the curve that went like this? Remember that thing? I'll zoom in. I just want to get you a pretty good image of this thing. Hold it down. Is it firing up? Let's see. All right. And when you remember the helix, the curve, check out this guy. That was the one I want to look at. It's like a spiraling staircase. Does someone say that? That thing's called a helicoid. So we're going to come up with a parametric representation of that. It's called a helicoid. Yeah, you think like helicopter. Well, it's called a helicoid. Well, we need two parameters to do it. Well, let's start with the helix. You remember what a helix was? A helix was a curve. And we parameterized that one, we used just a t. We did something like this. Cosine t, sine t, and just a t. You remember this? This allowed the thing to just circle around. Bless you. That was the parameterization of the helix. So this should look very, very similar. I'm going to use the variables u and v. All right, here we go. So how about I'll use v for all those t's. Like a cosine of v, and a sine of v, and a v. But now I need something that's going to make this spiraling staircase get wider and wider and wider as it keeps spinning around. So I'm going to use another parameter here. I like the u. Now notice this looks somewhat like the cone, but be careful. It's not the cone. So that's the helicoid. The spiraling what? Everyone see one of these walkways in real life, like in a museum? Which museum? Anyone know? Ever see this? Right there, you get that staircase. Walks around like that. It's like a spiraling ramp. It's a helicoid. But it's different from the cone. What was the cone again? Look at the difference. T cos theta. T sine theta. T. What do you notice? Just to see the differences. The theta and the theta, was this the theta? No. In terms of the helicoid, see how that was always the same? Kind of like the helix. Look at the helix. Ta-da. So I know it can be confusing. The key thing to notice, x squared plus y squared equals z squared here, but not in that case. Cool. And when unfortunately, when you teach Calc 3 as often as me, you start going out, you get home, and you work on a lawn, and look what you end up doing. You start cutting all your shrubs like helicoids. You don't see that right here? That's my front lawn. You see that tree right there? So see, it's like the helicoid right there. You see one like this? See him in the front? I got some what? Spheres in there? Up there I got some paraboloids in the front. But anyways, that's what you're seeing there, just these surfaces. Yeah, those are more like, I don't know, you could say those are more like some of their spheres or parabolas, but there's the helicoids. So hey, all right, we got them all down. Let's start with surface area. We're now going to work the surface area. Yeah, don't be like me. Like your shrubs at the helicoids. Trim those forever. All right. So now we're going to find the surface area. The area of some surface. So the formula that we're going to have to do when we come with the area of the surface actually involves something we did earlier in this course when we found the area of a parallelogram. It's the double integral of this magnitude of some cross product of two, they call them tangential vectors. So how about before we do that, let's just find the equation of a plane. Do you remember in chapter, it was section 12.5, you had to find the equation of a plane? Well, let's do that now with the planes written in parametric form. So I'll put this on the board, so I'm going to copy this. Let's try that. What if you have, this is number 2. U comma V, U cosine V, U sine V, V. And U equals 1, V equals pi over 2. So, what I want you to do, you find the equation of this plane right here. Or excuse me, this is a surface. Find the equation of the plane that's tangent to that surface. R of U comma V. So when they give you this surface, U cosine V, U sine of V and V. Does anybody recognize that surface, by the way? Which one of these is it? Well, I could add one to the list. Helicoid. Which one is that? Does anybody recognize the surface? That's the helicoid. So this is a helicoid right here. And we're going to find the equation of some plane that's tangent to the helicoid. But plane, to be tangent plane to a surface, it's got to occur at some point. That's the point. So this is, right here, we're saying this is a point. So maybe the hardest part of this problem is, I thought points were x, y's, and z's, right? Like an x, y, z coordinate. We're going to have to figure that out. That's probably the hardest part of the problem. When they gave me the u and v of a point, how could you find the x, y, and z points? How can you convert that point to Cartesian? That's probably the biggest challenge of the problem. How can you make it x, y, and z if you had to? If you wanted to do it, what could you do?
So x is the cosine, right?
There
Cosine
you
pi.
go. So this would be right here. I can plug these in. What would be the x component? Just so people can connect that. What's 1 times the cosine of pi over 2?
0.
0. That's why I want to see this, that this is like a problem from before. That's the x coordinate of the x, y, z, right? Triple here, that actual point. What's the y?
1.
1 times sine of pi over 2 is a, what's the v? Oh, just a what? That is the point we're talking about. That's that point. So it doesn't look all what? Weird. It's just a parametric representation. So we need to find the equation of the plane tangent to the surface. Well, do we have a point? Yep, and it's in the plane, isn't it? So when there's some surface, and we're coming up with this equation of plane. You got the point. What else did you need in chapter 12 in throughout the course? What kind of vector? You needed a normal vector. And when we needed a normal vector, that's the other thing you needed to get the equation of a plane. You got the point, but you need some vector that's normal to the point. So, how do we do it? We'll just get the cross product of 2 tangential vectors. We'll get the cross product of 2 tangential vectors that lie in a plane. Look, you get a vector line in a plane, another vector line in a plane, we cross them, we'll get the what? The normal vector. So this is the cross product of 2 tangential vectors. And that'll be our normal vector. So let's find it. You ready? R sub u. This is a tangential vector. I'll leave enough room. You got to get the derivative of this with respect to u. Keep in mind, we're trying to get this. That will be our normal vector. At the point in the plane, we need a normal vector. So we're working towards that. But to get it, I need the cross product of RU cross RV. All right, what's the derivative? Now we're doing partial derivatives. What's the derivative with respect to u?
Cosine V.
Cosine V. Man, you're good. What's the derivative with respect to u?
Sine V.
You're crushing these partial derivatives. What's this one? No trucks.
0.
Zero. I like zeros to make the math a little bit easier, right? What's this change on the vector? With respect to v. What's that?
1.
Okay. What's the derivative of that with respect to v? Be careful.
Negative sine, u negative sine V.
And you keep the u in front, right?
You know.
Negative u sine v. Is everyone okay with that? The partial derivative with respect to v. Excellent. And what's the partial derivative with respect to v? It's similar to this. Just u
U
cosine v.
cosine V.
So all we gotta do is cross these vectors and then substitute the point, right? Now this is up to you. I think it's easier because it's at a point, right? I think it's easier to substitute the values in here first and then cross them. So you get numbers. Does that sound good? So that's what I'm gonna do. Let's find what's RU at the point, what was it? R sub u at 1 comma pi over 2. And what's R sub v at 1 comma pi over 2? What I mean is, let's substitute these. Then we'll cross them. Then we'll take the cross product. So I'm going to plug a 1 and a pi over 2 in there. What do you get? Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And this was a what? 0. Now do R sub v. I'll just substitute them in there and into the tangential vector at that point. What's negative 1 times sine of pi over 2?